In this problem, we're given the Ka of a monoprotic acid, which is 7.58 times 10 to the minus 3. We're asked to determine the percent ionization of a 0.195 molar solution of this acid. So we want to remember that a percent ionization of any weak acid is how many, or what's the molarity of the ions that form at equilibrium compared to the original concentration of the undissociated or unionized acid. So we can either use the concentration of hydronium at equilibrium or the concentration of the conjugate base at equilibrium, compare that to the original undissociated acid concentration, which in this case is 0.195 molar, and then multiply it by 100% to get the percentage. So to figure out what the concentration of hydronium or the conjugate base is, we need to set up our ICE table. And here's the generic equation for the dissolving of a weak acid in water. The acid is going to donate a proton to water to form the hydronium cation and the conjugate base of the weak acid. We're told that we have 0.195 molar of our acid to begin with, and the reaction has to shift to the right to get to equilibrium. So that's why we have a negative X here. We're losing our concentration of HA, or not losing it, it's getting smaller because we've got to form some hydronium and conjugate base to get to an equilibrium situation. Remember that the coefficients of the X's refer to the stoichiometric coefficients in the balanced chemical equation, and they're all 1, so this makes this pretty easy. In our ICE chart, our final row is the equilibrium concentrations, and we get that by adding our first two rows. So 0.195 minus X is our equilibrium concentration of our acid, and then X is going to be the equilibrium concentration of both hydronium and our conjugate base. So if we plug these values into our equilibrium expression, we end up with X squared divided by 0.195 minus X equals 7.58 times 10 to the minus 3. Now our Ka is relatively large, so I'm going to guess that I'm not going to be able to use my 5% rule and be able to discount this subtraction here. So I'm going to have to solve this using the quadratic equation, and the first thing I want to do is I want to set up my equation so that it's in the form ax squared plus bx plus c is equal to 0. So the first thing I do is I want to get this part of my equation, 0.195 minus x, out of the denominator, and I do that by multiplying both sides of the equation by this term. So I end up with x squared equals 7.58 times 10 to the minus 3, this value here, and I'm going to multiply it by 0.195 minus x. So to simplify that, I've got to distribute. I've got to multiply 7.58 times 10 to the minus 3 by 0.195 and by negative x. And so when I get that, here are the two values that my calculator tells me. Now I want to get this in the form ax squared plus bx plus c is equal to 0. So I'm going to subtract 1.4781 times 10 to the minus 3, and I'm going to add 7.58 times 10 to the minus 3x to both sides of the equation. And now I have my equation in the form ax squared plus bx plus c is equal to 0. And that allows me to identify what my a, b, and c values are so I can use the quadratic equation. So according to my equation, a is equal to 1, that's the coefficient of my x squared. B is 7.58 times 10 to the minus 3, that's the coefficient of my x. And c is negative 1.4781 times 10 to the minus 3. So now that I've identified these values, I plug them into the quadratic equation. X equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. So a is 1, so I've just put 2 in my denominator here. And it's a little hard to see because it's so small, but the discriminant, b squared minus 4ac, I calculated as being 0.07705489212. And that's the value of the square root of b squared minus 4ac. So once I calculate the discriminant, it just makes the equation a little easier to handle. So then I take negative b, negative 7.58 times 10 to the minus 3, and I'm going to try adding the discriminant first. And so when I add this value, when I simplify this side of the equation, I get 0.0347. So my next root I'm going to solve by taking negative b, negative 7.58 times 10 to the minus 3, and subtracting the discriminant and dividing by 2. And when I do that, I get a negative value. So anytime we solve for x in these type of problems, one of the values will not work. Either it will be negative or it will be larger than the original concentration. So in this case, I know that this value of x is not acceptable because you can't have a negative concentration, and so I know that this root right here is the value of x, the solution to my quadratic equation. So I'm going to scroll down on my paper a little bit. Now that I have x, which remember is equal to the concentration of hydronium as well as the concentration of my conjugate base, which are the ions in this equilibrium process. Now that I know the concentration of these ions, I can figure out percent ionization. So the concentration of hydronium and my conjugate base at equilibrium is 0.0347. I divide that by the original concentration of the acid, multiply by 100%, and in this situation I get 17.8% ionized.